Hello everyone, welcome to my Your Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is Cousins in a Binary Tree Part 2. Okay, so you will be given the root of a binary tree, and you have to replace the value of each node in this binary tree with sum of all its cousin values. Okay, so for example, let's say this is the input that is given to you. Let's take the very first example. So for a particular level, okay, uh, th- basically for two nodes to be cousins, they have to be at the same depth of different parents. Okay, so by same depth, it means that at the same level. Okay, so if you divide your whole tree into levels, so it will be, let's consider this at the 0th level, okay, or 0th depth, and it will go on increasing the first level. Okay, and it will be the second level. Okay, so see, for one it is having cousin. Okay, basically it should not be uh, on the same, it should be on the same level, and it should be from a different parent. Okay, parent of that particular node, and one should not be same. So the only cousin that one would be having is 7. Okay, so you have to replace 1 with its cousin's value. Okay, earlier it was 1, now it is replaced to 7. Okay, similarly 10 will also be having only one cousin. See, 10 will not have one as is cousin, because the parent of 10 and 1 are is same, it is 4. So it should be a different parent, so it is 7 only. So that's why this 10 is replaced by 7. Okay, and see, for 7 it is having two cousins, which are from different parent but at the same level, which is 11, which is 1 and 10. Okay, and the sum of these two will be 11. So instead of 7 we will be writing 1 plus 10. Okay, sum of its cousins. Okay, so this is what you have to do for every node that is present in the binary tree. Now let's see how we can do that. Okay, and you have to return the basically the root of the modified tree, and there is a note that the depth of a node is the number of edges in the path from the root node to it. Okay, so how many number of edges it would be taking to reach a particular uh, node would be the depth of it. Okay, so to reach let's say 1. Okay, so to reach this particular node, how many edges you would be taking? 1 and 2, two edges you would be taking, so its depth should be 2. Okay, indeed it's 2 only. Okay, so anyways, let's try to think of an approach. Basically, to solve this particular problem, and before thinking of an approach, it is advisable to have a look at the constraints also. Okay, so according to the constraints, the number of nodes in the tree will be of order 10 raised to power 5, and each value will be of order 10 raised to power 4. Okay, so these are the constraints. So let's quickly think of an approach. So let me clear some things out. Basically, to solve this particular problem, the very first approach that came to my mind was that a level order would be required, because we are talking about the nodes at the same level. Okay, so let me draw these arrows so that you will be able to visualize correctly. Okay, and it should be resulting into this. Okay, so this will be your input, and this should be your output. Basically you have to return the root of the new modified tree, okay, or new root. You have to return this and you will be provided access to this, let's say old root or the root only, okay. So you will be given this as your input, okay. So how we can solve this particular problem? See, since it was mentioning that uh, we will be considering the nodes at the same level or the depth, you can say. So these are the same levels on which the nodes are at. So how many edges you would be traversing to reach the root? It would be 0 edge. So it is the 0th level, okay. And similarly it is one level and it is second level, okay, first level and second level, okay. I hope level concept is clear. Then see, we would be interested in traversing this whole thing level by level, so level order traversal will be used, okay. So if you are new to this particular thing, level order traversal, and you are hearing its name for the very first time, then it is a kind of a prerequisite to solve this problem further down the line. So I would highly advise you to go over to the link provided in the description box and familiarize yourself with level order traversal, okay. And also what you can do is, in yesterday's video also I have explained it, the level order traversal. I will be providing videos link in the description, okay. And so link for this particular video will also be provided, and please watch it from this particular timestamp, okay. The timestamp will also be mentioned along with the link of the video. There I am explaining the level order traversal. So I hope uh, you right now have familiarized yourself with the level order traversal, or at least you are having prior understanding of it, okay. So now let's see how we can use level order traversal to solve this, okay. So see, what we would be doing is, let's say while you are visiting a node in the level order traversal, let's say you are visiting one, okay. Let's take some other color. So let's say you are visiting one, okay. Right now you are at 1 and you want to know what kind of value we would be entering instead of 1, okay. If let's say you are having access of what is the sum of all the nodes at the current level, so if let's say you are having access of level sum, okay, what would be the level sum here? It will be 1 plus 10 plus 7, which will be 18, by the way, okay. So let's say you know that it is 18, okay. And you also know for each node what is the sum of the siblings, okay, including the current node. Basically since it is a binary tree, each node will be either having left child or right child, so only two nodes can share a single parent, okay. So what we will be doing is, we will be taking one variable sibling sum, okay. So sibling sum will be given for each node. It will be nothing but the sum of the node itself plus with its sibling, okay. So it will be 1 plus 10, okay. So these two are sharing the parent, so it will be sum of these two, okay. So this sibling sum will be available for each of the node. So for 1 and 10 it would be 11, both of them it would be 11, sum of these two, okay. And for 7 it would be 7 only, since it is not having any other sibling, okay. So this will be available. Now let's say this kind of information is available for every node, okay. And so it would be very easy to calculate you know, what is the replacement value, okay. So once you are having all this information, it would be very easy. What you would be doing is, simply you would be taking what is the level sum right now, okay, level sum minus the sibling sum, okay. So level sum is 18 and sibling sum is 11, so it would be 7. For this particular one it would be 7. So indeed it is the case that it will be 7, and we have inserted 7 here. Similar will be case for 11. Sibling sum, the level sum is 18, sibling sum is 11, and it would be 7. Okay, so for this particular one, level sum is 18 and sibling sum happens to be 7, so it would be 11. Okay, so this verifies the formula. Level sum minus sibling sum will be the kind of a formula that we would be using. The only thing that we have to add extra in the classical level order traversal technique or algorithm would be to just somehow keep information of level sum for each of the levels. Okay, for each level. Okay, and then for each of the nodes you should be having information of the sibling sum. Okay, so once you are having these two informations, level order traversal can be tweaked a little bit to solve this particular problem. Now we will be seeing how this particular logic will be applied in the uh, implementation. Okay, and for that I will be taking the code to the board. Okay, so this is the code. It's a bit lengthy, but be with me and we will be understanding each and every bit of it. Okay, so let me zoom in a little bit. Yeah, I think now it should be fine. So now let's discuss what's happening inside here. Okay, so what we would be doing is, since we talked about that we would be needing sibling sum for each of the nodes, so we will be uh, using a custom class. Okay, so modified tree node. Okay, the only extra information that each node will be carrying is its sibling sum. Okay, and the node's particular reference by default, whatever the node reference was. Okay, so this is just a constructor that I have defined to store the values of sibling sums, to initialize the value of sibling sum and the node. Okay, so each node is right now having access to sibling sum. Okay, so this is the modified node, modified tree node. Okay, so then the question arises how we would be storing this level sum for each level. So for that we would be using a map. So the first, the key will be the level number, or the value will be the level sum. Okay, so depth depth sum map, or you can consider it level sum map. Okay, whatever you may want to call it. Okay, the second, then our classical level order traversal begins here. So instead of queue, it's just my preference that DQ offers some more functionalities, but you can totally use queue also. Okay, so then we will be implementing a standard level order traversal and with some tweaks. So once you have declared the queue, so basically this what does this queue helps us to do is, let's say you insert the, let's say it is something like this. Okay, these are two levels. Okay, so the very first time you insert the root into the queue. Okay, and then you start your level order traversal. Basically each time you would be asking what is the current size of the queue. Okay, that many nodes you will take out of the queue. Okay, and that many nodes will be in the current level. Okay, so current size is 1, so you will be taking only one node out of the queue. Okay, now this node is gone, no longer here, and taken out. So then you would be asking this node, are you having any children of yours? So it will say yes, I am indeed having two children of mine. So you would be adding them to the queue. Okay, these two children. Okay, let's call this left and right. So this would make your one level traversal complete. So this level is complete right now. Okay, And the next time you would be asking again what is the size of the queue. So it is 2. So you have to take out 2 entries, and when you will be taking them one by one, taking them out one by one, let's say you took out this left. Okay, you will ask it, are you having any children? It will say no, and so you are done with it. Then you will take one another out because the size was 2, so you were supposed to take 2 entries out of the queue. Okay, so this way, level by level, you would be able to do the traversal. Okay, so this was just a brief explanation of how level order works, and if you uh, want a detailed explanation, as I discussed, head over to the description box and find the link of an article, or you can totally check a video upon it which I have made yesterday explaining level order. Basically it was a similar kind of problem and it was also requiring level order. So start watching from this timestamp, and that description box will also be having link for this particular video. Okay, so then what we would be doing, as we discussed, firstly we would be adding the root entry. So the root entry would be the modified tree node. Okay, it would be having two values. The first value would be the sibling sum. Okay, for the root it is having no sibling. Okay, so its value only will be the sibling sum, and then the original root or original node. Okay, and it will be your first entry into the queue. Okay, then you would be having one variable to define what is the current level, so that we can put entries corresponding to the level sum in the depth sum map. Okay, so for the current level, since you are having only root, so you will insert what is the level sum right now. So this is the level sum for the 0th level, level sum for 0th level. Okay, so once you have done that, then you will be traversing or doing operations on the queue till it becomes empty. Okay, so what will be those operations? As we discussed, firstly you would be asking what is the current size of the queue. That will be determining the number of nodes in the current level. Okay, okay, and then you would be initializing one variable, level sum. Okay, so once you have initialized that variable, you will start taking values one by one out of the queue. Okay, and you would be doing this level size times. Okay, as we already discussed. So you for each of the node that you would be taking out, you would be initializing a variable sibling sum. Okay, so what this sibling sum will do is, for you will initialize a variable sibling sum. Okay, and it will be set to 0. Okay, so 4 is having two children, and this sibling sum will be sum of those two. So 1 plus 10 it would be, so sibling sum would be 11. So while you have taken 4 out, for every children of basically 4, you would be adding, while you would be adding to them to the queue. Okay, you would be adding this sibling sum property also. Okay, so once you have taken a node, modified node out of the queue, okay, you would be taking the original node's reference. Okay, from the modified node, and then you would be, as you have already initialized the variable sibling sum, then depending upon whether it is having right child and left child, okay, you will be increasing the value of the sibling sum by their values. Okay, so once you have done that, then uh, we would be asking again if the node is having the left child and the right child. If it is having the left child, then it would be added to the queue, as we already discussed. So while taking some node out of the queue, you would be asking, are you having some children? And if yes, they would be added to the queue. Okay, so in that particular this is what we are doing here. and we have already made the value of the sibling sum. So a modified tree node will be pushed if left and right child are available for current node. Basically, level order, what you do is, while you are taking one node out of the queue, you are trying to make one level below it. Okay, so this was the whole logic of using this size variable, uh, basically this level size. Okay, this is what it will be helping us to do. Okay, and once you have done that, done all of this, then for the current node that you have taken out, you will try to see what value you will be doing. So here will be the replacement part. So here you will be doing the replacement. So for the replacement, what you would be doing is the level sum minus the sibling sum for the current node. Okay, whatever will be that value, you will be assigning that to the current node that you have taken out. Okay, and now on top of that, while you are doing this thing, you will also be forming the next level sum. Okay, so basically, while you are, you know, traversing the current level, you should be making the information of what is the level sum for the next level also available. So for that particular purpose, you have initialized this particular variable next level sum. Okay, and depending upon whether the current node is having the left child and the right child, you will add their values to the next level sum. Okay, now once you have done all that and you have traversed the current level, then you will be adding a entry corresponding to the next level and its sum. Okay, so here your current level will also be incremented, and next levels sum will also be offered to the depth sum map. Okay, because while traversing the next level and making the replacement for those nodes of the next level, you would be needing it. Okay, so we have provided it on one previous level only. Okay, so then once you are done with all this level order traversal, this whole thing, then your root of will be representing the modified tree, and you will be simply returning that. Okay, so this is the whole logic and approach. If you are still having any kind of doubts or any queries in general, then you can ask them in the comment section. And as far as time and space complexities are being concerned, the time complexity wise, let's take a different color here. So time complexity wise, see how many entries can be there in the depth sum. It would be able, it would be equal to the depth of the tree. Okay, uh, okay, and basically each node will be only processed once. Okay, so you are processing each node one by one. So the whole time complexity will be order of n if there are n nodes in total. Okay, so if there are n nodes in the whole tree. Okay, and space complexity wise, you are using two structures here. The first structure is the level queue and the second structure is the depth sum map. Okay, so see how many entries at worst case would be there in the level queue. So it would be order of n only. Okay, and depth of the whole tree would be either less than or equal to uh, basically of order n only. So these would be the time complexities. Okay, so if you are still having any kind of doubts or any queries in general, then you can ask them in the comment section, and I really hope this solution walkthrough added some value to your journey of honing your DSA skills. Keep solving more and more problems, and I will be seeing you in the next video. Thank you for watching.